So here are your instructions for how to predict molecular geometries. So first of all, draw the Lewis structure for the molecule. If you need help with that, refer to separate instructions on drawing Lewis structures. From the Lewis structure, determine the total number of electron groups on the central atom. Determine the number of bonding groups, the number of lone pairs. And then I think this is the most ridiculous thing. Refer to table 10.1. Well, that's great if you're doing homework, but what if you're taking an exam? I am not going to give you table 10.1. I'm not. So these are my instructions. Think about balloons, how balloons would arrange themselves. And then imagine that the lone pairs are invisible balloons and name it accordingly. That's why I went to all the trouble to do all this balloon business. Okay, let's predict the molecular geometry and the bond angle for ClNO. What do we have to do first? Draw the Lewis structure. So this is a weird looking molecule, and we are like, I don't know which one should be in the middle. Actually, for geometry, it doesn't necessarily matter so much, but oftentimes the formula and how it's written is a clue. So ClNO, we want you to put the nitrogen in the middle and the chlorine on one side and the oxygen on the other. So here's Cl, N, and O. Okay, so we got to get the correct number of valence electrons. Chlorine has 7, nitrogen has 5, oxygen has 6. Add those together, we get 18. So we just start distributing electrons. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Ran out. What do we do? Make a double bond. Okay, so let's take a lone pair from nitrogen and share it with the oxygen. That's not nitrogen. So chlorine has an octet, nitrogen has an octet, oxygen has an octet. Everybody's happy. Is there another way we could fulfill octets for this? We could put the double bond on the other side. So let's investigate that. How would we tell which one is better? Formal charges. So remember, the shortcut for formal charges is halogens like chlorine like to have one bond. So there it's got one bond. Nitrogen likes to have 3, it's got 3, and oxygen likes 2, so it's got 2. These all have 0 formal charges. Over here we've got chlorine with 2 bonds and oxygen with 1. The nitrogen still has 3. And if we calculate formal charges, remember what we did there? We think about, well, let's break up this molecule. Chlorine brought 7 electrons in. If we break it up like this, it'll take 6 home. 7 minus 6 is plus 1. So this would have a positive 1 formal charge. The nitrogen brought 5, it would leave with 5, that's 0. The oxygen brought 6 and would leave with 7, and so that's a negative 1 formal charge. So these formal charges are larger in magnitude than the zeros, and so we're going to reject this one. Turns out it doesn't matter for the molecular geometry, but a little review. How do we figure out the geometry of this?
The electron geometry and the electron.
Well, we have to start with the electron geometry. So we count what?
How many
Electron groups. So how many electron groups? How many electron groups? It's not 4. 3.
Double bond.
Double bond is one group. It's not electron pairs. It's electron groups. Okay, so 3. I'm actually just going to get rid of all of this so I can draw a picture. So what shape do 3 things do? Trigonal, pyramid. No, trigonal planar. So three things, three balloons would get away from each other like this, and the bond angle, they'd all be the same, it'd be 120 degrees, right? So the electron geometry is trigonal planar. Let's call that EG for electron geometry, trigonal planar. But it's asking us for molecular geometry. So molecular geometry, then, we start with the electron geometry, and we make invisible things that are lone pairs. So we've got one lone pair. So let's make that invisible. And so then our molecular geometry is bent. Oops. Molecular geometry is bent. And if it makes more sense to you, you could put the lone pair up there. So what does that do to the bond angle? This is the bond angle. This is the bond angle we're interested in, because it's where the bonds are. This angle we don't really care that much about, although it affects this angle. So what's this bond angle? Is it 120? No, it's less than 120, right? Because this is very repulsive. He's disgusting, he's gross. And so these guys would rather get a little closer to each other to be further away from him.
116.2.
I don't know. Less than 120, and this one's going to be greater than 120. They still have to add up to 360. Any questions? Let's do another one. Predict the molecular geometry of I3 minus. Well, we'll start with our skeletal structure. Sticking those iodines in a line. We have to count valence electrons. 3 iodines, they each have 7, so that's 21. And then we have to add 1 for that negative charge. So we've got 22 valence electrons. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Where do I put those last 2? On the central atom. Just squeeze them in there. It's like, well, that looks ugly, so I'm just going to move them over a little bit. So I've got 2 lone pairs over here and 1 lone pair up there. And then to complete this, brackets and a negative. So we've got our Lewis structure. What question do we ask ourselves?
What are we doing?
What are we doing? Why did I sign up for this class? Why am I still in the class? Why didn't I drop the class when I had the chance? How many electron groups around the central atom? How many are there? 5. 5 electron groups. 5 electron groups. So 5 balloons. How do 5 balloons arrange themselves? Trigonal bipyramid. The electron geometry is trigonal bipyramid. Bipyramid just means 2 pyramids. Okay, so let's draw that. Okay, trigonal bipyramid. So then lone pairs. We need to indicate which of these things are the lone pairs. Trigonal bipyramid, remember, we've got different angles here. We've got 90 here, and then 120 between the equatorials. So where do those lone pairs go? They go around the equator. So these guys become lone pairs. Little girl took off her tutu. She has a leotard on, it's fine. What's the molecular geometry?
T shape. Oh wait, I forgot the other one.
I could go for I-shaped, but it's linear. You guys are so much more fun than the Monday, Wednesday class.
You would probably get upset if they watch your videos on us.
Well, maybe they would, but then they should hear you guys and they should understand. I like them too, but you guys are just more fun. So that's
I'm
linear.
impressed listening to your Monday, Wednesday lecture. I'm like, Lord.
I know.
Dropping all these jokes, and there's like no chuckle, no.
What can I say?
LOLs, no
What can I say?
Is this part going to end up on the YouTube videos now?
I'm still recording here, yeah. This discussion, yeah.
The Monday, Wednesday class?
I left the does this structure bother you thing off, but this is on here. What's it doesn't ask us, but what's the bond angle here? 180, so 180 degree. Any questions?
So this ends up being linear.
Linear. Mm-hmm. Okay, so a lot of these are three-dimensional, and that is challenging to represent on a two-dimensional surface, whether it's a tablet screen or a chalkboard or a piece of paper. So this is what we do, what scientists do. We use a straight line to indicate a bond that's in the plane of the paper, and we use a pointer with a mind of its own. I don't know what it's doing. It's still jumping around on my iPad. I've got 3 screens that I'm looking at. It's confusing. A hatched wedge, kind of like a dotted line, that's behind. So if the screen is opaque, you can't really see that, right? It's just a dotted line behind the screen. And this is a bold, solid wedge. This is jumping out at you. Okay? So if I was going to draw like methane and make it three-dimensional, it's tetrahedral. And so I draw these 3 in the plane of the paper. You might as well get as much of it flat as you can. And then this one's going to be sticking out at us. And this one is going behind. You don't see it or you don't like it?
I don't like it. I see
But do
it.
you see it?
I just don't like it.
Anybody not see it? I can live with you not liking it. You come up with something better?
No.
Yeah, see, that's the problem. You can complain about my stuff, but you can't do it any better. So it's like this. These 3 are in the plane. This one's sticking out in front, and this one's behind. What if we have larger molecules? What if it's not just one central atom with some stuff hanging on it? There's lots of things like that. What we do is we look at the geometry around each interior atom separately. And this is very definitely a precursor to OChem, which I know that some of you are going to be taking. You have to be able to look at the geometries here in OChem. So here is our Lewis structure for glycine. Glycine is one of the amino acids. It has 4 interior atoms, nitrogen, carbon, carbon, and oxygen. The hydrogens and this oxygen are terminal. We're not going to look at them. They're just the thing hanging off the side. So we look at the oxygen and we say, how many electron groups? 4. So that's a tetrahedral, but there's 2 lone pairs, so it's bent. So this is a bent, and this model is depicted with that bent. We look at this carbon. 3 electron groups, right? Double bond and 2 single bonds. What does that make? Trigonal planar. There's no lone pairs. So that's trigonal planar. Here, this is a triangle. Over here, this carbon has how many groups? 4. 4 groups is tetrahedral. So here it's tetrahedral. This one's coming out at you, and this one's going behind. The nitrogen also has 4 groups, but it has a lone pair. And so that's a trigonal pyramid. Yes.
On these, whatever bally thing you call them, Is there ones where there's 2 bonds listed? I guess you don't really need it, huh?
Yeah, I'll show you. I'll show you how that works. So let's do one here. This is acetic acid. Predict the geometry about each interior atom and make a sketch of the molecule. You've got to start with the Lewis structure. So this is a structural formula where we're showing a double bond and how these things are connected, but we need a little more detail. So I'm going to show that there's a bond between this oxygen and this hydrogen. So there's a bond over here, and here's the hydrogen. When we see H3C, what we're indicating is that those 3 hydrogens are all bonded to the carbon. And there's not really any other options because the hydrogens can't make a chain because they can only form 1 bond. So I'll take those and draw them out better. Okay. So there is the beginning of our Lewis structure, and then we need to put the electrons in. And I think you guys have figured this out by now, so I'm not going to... Ooh, that's really big. Well, it's really big because it's really small. That made a lot of sense to me. Okay, there's our Lewis structure. Well, let's start with this carbon. How many electron groups on this carbon? 3? 4. You weren't looking at the one I was pointing at. That was 4 electron groups. What's the electron geometry? Tetrahedral. Are there any lone pairs?
No.
No. So the molecular geometry there is the same. So this carbon is tetrahedral. What about the other carbon? How many electron groups? 3. Any lone pairs? No. So what's the geometry on that one? Trigonal planar. The good news is that the tests are written, and so you don't have to pronounce it correctly. Yeah. Okay, the oxygen. How many electron groups?
4.
4. So 4 would be tetrahedral, but 2 lone pairs. No. So it's electron geometry is tetrahedral. So without moving them, you pull off 2 of those atoms, and that's not linear. Bent. And that's very important. Okay, so this one is bent. So you need to be able to do that. Making a sketch, I would expect you to have some trouble with that. So making a sketch of that, I'm going to put as much of it as possible in the plane of the paper so I can minimize the things sticking out. Okay, so I'm going to start over here with oxygen. Here's the hydrogen, and that's like that to the carbon. So this is bent, and it's supposed to be less than 109.5. So I don't know if I got that right or not. Close enough. And then this one is trigonal planar. So that's 120-degree angles. So I'm going to try to spread those out. And here's my oxygen. This is another carbon. And then this carbon down here is tetrahedral. So I'll stick one over here, and then the others have to be out of the plane of the paper. So there's a sketch. Ew, yeah, exactly. Any questions?